In the previous video, we looked at binomial implementation or Cox-Ross-Rubinstein binomial tree using dynamic type implementation. And when we say dynamic, we really we're referring here to the use of memory. Code that I've developed here is partially from Espenhogue. We took some VBA XL code from Espenhogue, and we mirrored fairly closely its implementation in C++. So at the base of the Espenhogue idea is that when we develop the estimation in the tree, the binomial tree, we estimate the stock price in arrays. So basically we generate initially the final array of stock prices, so that at the terminal nodes we generate the stock prices, and then we estimate the intrinsic value of the options. And as we do backward recursion, we basically destroy the preceding values, so we go backwards. With the static binomial tree, the implementation using this type of C++ iterative loop was that you generate the stock prices, and then you generate all the stock prices in the tree and you hold them in a kind of static memory. And then as you as you perform backward recursion through the tree to estimate either the value of the European or American option, whether it's for the call or for the put, we make reference back to all these values that are stored in the tree. Where Espenhogue differs is we estimate the value of the stock prices, and we estimate the value of the options, and as we pass back through the tree, as we do our backward recursion, the preceding values are binned, and these newer values then become the relevant values. To demonstrate that a little bit in terms of our own code here, we go into the binomial tree. The usual include libraries are invoked. We also invoke libraries for time, estimating the time the estimation takes, so time.h. We've set out the function where the parameter inputs include the number of steps in the tree, the current stock price, the exercise, the risk-free rate, the dividend, the volatility, the maturity of the option, whether the option is put or a call, and then the option style would mean whether it's American or European. We then have to declare values in terms of what kind of format. Are they double? Are they a float? Is it a character? Are they integers? So on. We estimate the Cox-Ross-Rubinstein estimates of the time step, the value of u in the Cox-Ross-Rubinstein tree is e, and then the exponential, and then we take the power of sigma by the square root of the time step. D here is just the inverse of u, and p we have, which incorporates dividend yield, is the risk neutral probability, and we invoke u and d in this estimate here. I follow Espenhogue here. If the put call character is a call, then C, then Z is equal to 1. If it's P, Z is equal to -1. We'll see why that's relevant in a moment. And then because we declare a vector, it's a double, it's a single array, not double dimensioned, and because it's resizing or because it's dynamic, we make this declaration here. And then at this, when we estimate the value of the option, then initially we start, unlike the static tree, if we go to the static tree for a moment, we built the tree, we generated all the Sij, so each stock price was grid reference with an I and a J, and we estimated the entire tree, right? So all the nodes in the tree are estimated and stored. The approach here in the dynamic tree is we don't estimate the tree quite like that. We estimate initially the intrinsic value of the options, and that's for if it was a call, we'd have the maximum of 1, and then S minus the exercise, or the stock price minus the exercise, or 0, whichever is the greater. And so that implies all the negative values fall out to 0. And then the value of the stock price is estimated by taking SU to the power of S multiplied by U to the power of I multiplied by D to the power N minus I. So basically, if we go into our Excel spreadsheet, when we're estimating the stock prices, we start here at the bottom and we estimate going up. So the value of I is going from 0 to N, and once J is declared, J is just 5. And so if we go back to the code again, in our dynamic tree, then I goes from 0 to N in increments of 1, and we keep adjusting. So D initially is, we take N. If I is 0, then D to the power of N, the number of steps, and U to the power of 0, which is equal to 1. Okay, so we estimate the intrinsic value of the options, and they are stored. And then to perform the backward recursion, we then go to J starting at N minus 1. So again, basically, we're starting at this node here. So N minus 1, if N was equal to 5, if J is equal to 5, then N minus 1 would be equal to 4. So we have, starting then with going backwards, J is equal to 4, and it's going to go backwards in steps of 1. And once we have J equal to 4, then we start with I equal to 0 up to that 4. So again, if we look at here, we have J is equal to 4 and I is equal to 0 to 4, and we go in steps of 1 from 0 to 1 to 2 to 3 to 4, and we estimate the value of the option in ascending fashion for that particular array. So going back into the binomial code, we're estimating I is going from 0 to 4. And if the option is European, we do backward recursion where we take the preceding values. In this instance, it would be the intrinsic value of the option. And we, if you like, discount by the risk neutral probability of P and 1 minus P respectively, and then discount in turn by e to the power negative risk-free rate by the change in time step. So once that action is performed, if it's E, we estimate the European. Once that action is performed, then J adjusts down, N, instead of it being 4, it now will become 3. So going back into, so J becomes 3, and I goes from 0 to 3. I goes from, if J is equal to 3, I goes from 0 to 3 in increments of 1. And again, we perform the same analysis taking the preceding values. So at each point, the new value of the option value is replacing the former. And in that sense, we don't leave a tail. Once the estimation is being performed, these values are being destroyed. Once we pass these values over here, these values are gone. And likewise, once we pass these values here, these values are gone. And that's a much more efficient use of memory, and that continues right till we get to the end. Okay, if the option is American, then same process, except we add one additional consideration in. Is the intrinsic value of the option greater than the time value? And if it is, we take the intrinsic value. And if the intrinsic value is higher than the time value, that triggers this early exercise. And that feature is the else. So if it's E, if the up style is E, we apply the backward recursion simply with this algorithm. Otherwise, if it's not E, it's American, and then we have to make a choice at each interval, at each node. We look at the value, the time value of the option, and we compare it against the intrinsic, and we select the highest. Okay, and we keep going until the option value goes back to option value 0. So that's equivalent to coming here at this point here. Okay, now when we run the estimation, again we can take the step size down to previously we'd done 15,000 steps. We got this value, which is consistent with what's in Brody Temple 1996, 9.066. In fact, if we reduce the estimation down to 5,000, okay, delete and 5,000, take these values here and run. Again, we should get close to the 9.066. We would also like to observe the time that it takes for the estimation. So it takes 2.64 seconds. And the value we get for the option for the call using these parameters, the American option, is 9.0657. So close to Brody to Temple. If we had taken the static estimation and included these values, which I have here, and we run, again we should recover exactly the same time value. We should recover the same value for the call. The only difference should come in terms of the estimation time taken. Again, the static tree implies that we must generate all the nodes in the tree. All the nodes have to be estimated and stored. And again, when we look here at the estimation time, the value we get, the 9.065767, is the same value that we have obtained here. So in that sense, both are equivalent. 9.4, last digits are 9.4. This estimation took 2.64, so the binomial estimation, binomial dynamic, takes 2.64 seconds, but for the static estimation we're up to 6 seconds. And again, the savings in terms of time tends to increase as we increase the step size. So for instance, if we change this to 7,000 and run here, and I go back to the static, this model here is the static binomial tree. If I increase this to 7,000, the difference, the savings in time that we obtain when we run both estimations. Okay, so in the binomial tree, the estimation's still running with 7,000 steps. Okay, with the dynamic tree with 7,000 steps using the same parameter values as Brody to Temple 1996, the estimation time is now 5.71 seconds. Okay, so the estimation hasn't changed that dramatically, 9.06. Here on the static, the value hasn't appeared yet, so I'm going to just pause for a moment and wait until the value to be processed. Okay, so as happened before, when we ran n equal to 15,000, here with n equal to 7,000 using the static tree, the estimation has been aborted. Okay, so again we demonstrate that the dynamic tree is much more efficient and faster, even though it yields the same results.